chairing as a professor in the Department of Civil Engineering and a convener. He has been the convener of interdisciplinary program on climate studies in IIT Mumbai. His lecture at this occasion is sponsored by the NMHS funded project titled Pine Oak Systems Interactions between Climate, Water and Plant Biodiversity. The lecture would focus on the multi-scale variations of Indian monsoon impacting land processes over the Indian subcontinent. Moreover, this lecture will be highlighting the quantification of feedback processes from land to monsoon in terms of estimated recycled precipitation with information theory-based process network. The information theory approach is also adopted in the NMHS Pine Oak project for better understanding of eco-hydrological processes at multiple spatial scales. Largely, the lecture is expected to benefit the researchers and students of the institute, particularly in so many centers and as well as regional centers. So with this, before moving forward, I would like to request Dr. Sandeepan to tell more about our today's eminent personality and speaker, and then that will be followed by the lecture of Professor Ghosh. Dr. Sandeepan.
Thank you, sir. Thank you for your opening remarks. Before we start the presentation of Professor Ghosh, just to introduce Professor Ghosh, he is a chair professor in the Civil Engineering Department of IIT Bombay. He is also head and convener of climate studies in IIT Bombay. Amongst his many accolades, he is a lead author of IPCC AR6 Working Group 1. He is the recipient of Santi Swarup Bhatnagar Award, Sarna Jayanti Fellowship Award, and Boy Scout Fellow. He is now fellow of American Geophysical Union. Recently, he has received Devendra Lal Medal from American Geophysical Union, and he has also supervised more than 40 PhD students. And we are lucky to have him with us because he's also one of our PIs in a Pine Oak project where we are working on many aspects. As also said, with students who are working on the network theory to see eco-hydrological interactions between pine and oak system. So it's a brief introduction of Professor Ghosh. I have not said how many publications he has made and all, but thank you, Professor Ghosh, again for visiting us. We are looking forward to this interaction for a long time. So thank you, sir. Thank you. Now it's up to you, sir. You want to go towards the screen? Okay. ये तो काम कर रहा है कोई बात नहीं ये ठीक है सर
Thank you so much, Dr. Kunial and Dr. Sandeepan, for arranging this talk and for a kind introduction. Yes, and thank you for arranging this. This is an honor for me. So today I'll be talking on. Am I audible?
Yes.
So today I'm talking more on land atmospheric feedback on Indian monsoon with statistical and dynamical approaches. So when I'm talking about land atmospheric feedback, let us try to understand what does it mean by land atmospheric feedback. So when we say that climate change impacts or any impacts of climate variability or impacts of a specific weather, what we are more interested in understanding is that if there is something happening over the atmosphere, what is these impacts on the land, like how the water resources are getting changes and so on and so forth, and how the vegetation gets changed and so on. But land atmospheric feedback specifically means that whenever there are certain changes in the atmosphere, in the land, maybe because of atmospheric processes or maybe because of many other things, maybe because of human management also or anthropogenic activities, what sort of feedback it gives to the atmosphere. Let's say if there is a drought-like situation is taking place, what will be the feedback of drought to the atmosphere. So this sort of information, or there is a vegetation water stress, what will be its feedback to the atmospheric processes. So when you're talking about this, we have to essentially talk about land atmospheric feedback. This is slightly non-intuitional because we cannot really visualize very clearly how land is sending feedback. But here in this talk, what I'll try to show is that I'll try to show that why it is important. And this is one of the neglected area of Indian monsoon. Before 2010, people even I mean, monsoon was always believed to be a impact, or to be a process which is driven by large scale circulations. So local processes were always neglected for monsoon, and hence this is kind of very important to understand what will be the feedback from land to atmosphere. And this is the work which is done by many of my PhD students at different levels. So I've tried to pick up some of the work so that I can give some ideas what exactly we are doing in terms of land atmospheric feedback. Oh, sorry. So when you're talking about land atmospheric feedback, why land atmospheric feedback is important? So I'll go to one of this paper which is by Stephen et al. In 2018. This one was published in PNAS. So what Stephen et al. Was saying is that your Earth is going through different, Holocene, Anthropocene, and so on. Now we are in Anthropocene. That means when the anthropogenic activities are quite high. Now, and we are also seeing that we are very soon reaching some kind of a threshold. And after this threshold, what will happen? We'll probably reach certain condition from which we'll not be able to come back to our original condition, or some sort of here. Where are we now? So this is essentially the planetary threshold. So under a stabilized condition, let's say if you reduce your emissions and everything, probably will reach here. But the way we are going, probably will reach the threshold, and after that new state will come. And Stephen et al. Named this one as hothouse Earth. And one of the very important scientific hypotheses he questioned, or he has put, what he has said is that now we know we are not able to really visualize the land feedback to atmosphere. But what he has started saying is that, let's say when you cross this planetary threshold, the importance of land feedback will be very, very important, because this will be driven by the feedback, which is actually very important. And hence we need to really understand what are the impacts of land processes on the atmosphere. Now, if you really need to understand the land processes on the atmosphere, we also need to understand the trajectory or the perturbation in the land process itself, and which is again another challenging task. And hence, and this is one of the challenging tasks, because when you're considering land and atmosphere together, entire land, biosphere, atmosphere, and hydrosphere, all three spheres, when you're really considering together, then you need to really go for Earth system modeling, which has all the components. And it is still a challenge to really understand what is the trajectory of the ecosystem, because many of the processes in the ecosystem are not really very well understood. This is one of the very sort of a whole kind of thing where there are a lot of researchers needed to really understand how biosphere is interacting with climate, or what will be the climate impacts on the biosphere. This came in 2018. Bonan and Done wrote a very nice paper it came in Science, where it was mentioned that yes, there is a stress because of, so it has been mentioned that global change has put a lot of stress on the biosphere, and this will affect the climate trajectory also through feedback. This is very important. Biosphere is one of the very important component, which was not somehow it didn't get much attention in the climate studies till 2000 or so. After 2000, of course, it has got a huge attention. But still, the future direction should be in climate community should be to understand what is the Earth system prediction, including the biosphere. So biosphere should be a very important component of climate system. And then there were few papers. One of the paper is very, very famous paper by Ukkola et al. In Nature Climate Change, where it was, this was first few paper which talks about carbon fertilization and its impact on the vegetation. So what it was mentioned for Australia, that these are essentially first few papers. Of course, now we have a lot of papers on carbon fertilization and so on and so forth, and impacts of climate change, and how does it affect the carbon cycle. So where Ukkola et al. Has said that when there is an increased carbon dioxide, there is a limited precipitation threshold for vegetation, because its water use efficiency gets improved, and that results into greening. And when there is a greening, the moisture intake further will increase, and that results into decreased runoff. So it's not just water use efficiency is increasing. That doesn't mean that water extraction will reduce because there will be a lot of greening. So again, vegetation needs more water. In that way, there will be a decreased runoff. But this is only in the water stressed regions. And there are some observation data from Australia. So this shows that probably these things are very important. Of course, there is a lot of debate about this paper. After that, there is a lot of debate whether how the carbon fertilization will change the vegetation, whether there will be really a improvement in water use efficiency or not. If there is a water use efficiency, then does that really translate into greening or not? So there are a lot of debates on that. But this is a very important area, highly, a potential area of research, but still there is no very good scientific answer to this kind of questions. Now, I'll tell you why land atmospheric interaction is important. There was a very nice paper by Schaefer and Carpenter long back in 2003. He wrote a very nice paper. What he is trying to say is that why land component is very, very important. And this is one of the very nice paper to really understand what is happening. I like actually this paper when I started reading about it. It's trying to say is that, let's say this is the actual precipitation over a local region. And this is the global climatic factors that affects the precipitation. And let us consider that region has a lot of vegetation. So because vegetation also contribute to the precipitation, and because of vegetation there are a lot of temperature variations, etc., because of which you get a lot of rainfall, and this probably follows this curve. And this is the precipitation threshold below which you cannot really have a vegetation. So below this precipitation, local precipitation level, you cannot really have a vegetation. So what he's trying to say is that, look, if you have a vegetation, let's say your global climatic factors are changing, and because of which your precipitation is reducing, and finally when it's reaching threshold, then there is below which there is no vegetation. There is a huge tree mortality and so on. Vegetation gets reduced. And suddenly there will be a jump because system will break down. When the system will break down, suddenly it will go here. So probably without vegetation line is something like this, and with vegetation line is like something like this. So when it crosses the threshold, suddenly there is a huge change. So this threshold is important. So this is just an example. It can be exactly opposite also. So the point here is that when you are changing when you are actually crossing the threshold in a climate change scenario, your scenarios get changed, your feedback system gets changed, and that may have a huge implications. And somehow we keep on neglecting these things. We keep on saying that because of climate change, the stream flow will be changing, this will be changed, that will change. But we keep our ecology, we keep our biosphere remains the same. The same vegetation file we use for next 100 years and so on. And this is one of the major area which we really need to look into. Otherwise, all our climate change projections will have serious uncertainty and error. And this one we have to understand. There is the same Schaefer. He is a very good scientist. He wrote another paper in 2012. This was kind of a perspective paper. This is the paper where he introduced the importance. He introduced the network theory, why it is very important to understand an ecosystem or biosphere. So what he is trying to say is that if you are using a conventional approach, what we consider normally do is that there is one system that sends something to other system and so on. So there are small networks. Essentially, one is connected to another. But we do not really consider a network kind of system. So what happens when there is a stress, environmental stress, one by one the links get failed. And when the links will get failed, we'll see the system performance going like this because of stresses, the links are failing one by one. So your typical state stress curve looks like this. Now, but he said that, if you're looking at a system, if you consider a climate system, which is essentially consists of 4 spheres, atmosphere, biosphere, hydrosphere, and geosphere, and each of the sphere, there are small components, and all these small components are connected with each other. So actually, it's like a network. And what happens when your stress increases? Now what the system will try to do, system will try to generate more links to resist it rather than failing. So it's very similar to something like this. Let's say if you're considering some region let us consider a river in a hilly region. When there is not much of current, let's say 5 friends, 5 of you are actually crossing the river. So what you can do, each of you can individually cross the river. But when there is a huge current, what you will try to do, you'll try to hold each other's hand to cross the river. In a climate system or in a natural system also it's like that. When there is a lot of stress, what happens? They start holding each other's hand. So they generate more and more number of links. I'll show that with our analysis also we have found it. So they will try to generate more and more number of links. When they will start generating more and more number of links, what will happen? They will try to resist, and when they will try to resist, you cannot really see the failure. But once the threshold of the stress is reached, when it is reached, then what happens? The entire system fails. All the links suddenly fails, and there will be a sudden drop, and that is called essentially the complete failure. So now if we consider both of these things, it is very similar to something like this, which is again by Shepard and Carpenter tree in trends in ecology and evolution. So what it is being mentioned initially, let's say if it is in this kind of stage where there is a perturbation, it's getting changed, so it can go here and again come back, so it's not a threshold. Now if the system gets too much changed or the stress is very much increased, then if it goes here, of course it can come back, but that needs a lot of effort. Now if you are considering here to here, if the system is further changed, then it can go back, still it come back, it needs even more effort, but after that it cannot really come back. Its new stable condition will be like this. So that is what is tipping point. So you are crossing the change and its stability system gets changed, stability condition. And during this time the feedback becomes very important. So understanding of feedback is very important to understand this kind of stability, when this failure will take place and what will happen after the failure. Yes, now I'll come back to Indian summer monsoon. Indian summer monsoon rainfall is a subject, or is a topic where large scale circulation got a lot of attention. Of course they are important because monsoon is a part of large scale circulation. Yes, that is important. But what happened? The local scale factors were always neglected. So I was doing some work long back in 2012, 10 years back, and then what we have suddenly found, of course we all know that extreme rainfall is increasing, but what I am more interested in understanding the spatial variability of extreme rainfall. And what we have found is that the spatial variability of extreme rainfall has also increased. That means the rainfall pattern of one region is becoming much more and more different from the neighboring region, which is very important. So what we are not saying that everywhere the extremes are increasing. What I'm trying to say is that the extreme rainfall over here will be much different from its neighboring region. And that sort of things are happening consistently over the entire India. And you can see that everywhere the extreme rainfall, spatial variability of extreme rainfall is increasing if you're considering just central India or if you're considering the whole India. And that is only possible when the local factors will become important. Otherwise, because of large scale factors, you should expect a similar kind of changes. When the differences are increasing from one region to another, one is that different regions are responding in a different way. The second thing is that also means that the local factors are really very important. For all the cases, the local factors are important. So we hypothesize that local factors are important. Let's try to understand the local factors. So when we need to try to understand the local factors, we are essentially is a water cycle, and we are always give importance to this one. Ocean will generate a lot of moisture that goes to some circulation and it results into rainfall and so on. But what we do, we always neglect this part. From the land also a lot of evapotranspiration is taking place. And what exactly happens to this evapotranspiration, or what can we say about it? So one of my student, Amay Pathak, who is now a ASM professor at the IIT Kharagpur, so he was trying to understand that what will be the quantification of this precipitation which is generated from its own evapotranspiration. So let's say if you consider this region, this is one of the region, and let's say evapotranspiration is taking place over this region. Now if you are considering the total moisture over this region, some moisture is coming by advection from nearby regions and some are being generated by its own moisture. Now there is a concept which is known as recycled precipitation. Recycled precipitation means the precipitation that is being generated because of the evapotranspiration that takes place over the same land region. So we are trying to understand the precipitation that is being generated from this region's own evapotranspiration, and that is known as recycled precipitation. And the ratio of recycled precipitation to total precipitation is known as recycling ratio. So we are trying to understand the recycling ratio. Of course, if you consider the atmospheric moisture budget, and then you need to apply a computational fluid dynamics technique, which is known as Lagrangian approach. In Lagrangian approach, what we try to do, we try to track the moisture and find out where is its source. So we did some derivation. Of course, we collaborate with also some few of our colleagues who have been working from UIUC. One of our IIT Bombay alumni, only Professor Praveen Kumar, he also has been working on theoretical development. So we together sat together and then we developed for Indian monsoon. And then what we found is very interesting. This is the recycled precipitation figure. Now just look at this middle one. This is the recycling ratio. That means the ratio of recycled precipitation to total precipitation. You can see that initially the recycling ratio is quite low, but if you are considering the Himalayan region, there is a consistently very high recycling ratio. Specifically, if you consider this region, so these regions actually the biosphere is playing a major role in terms of generating rainfall. But important part is that you can see here that during the June the recycling ratio is quite low. It's around 10%. But as the monsoon progresses, you will get a high recycling ratio of 25%. 25% is a huge amount. In terms of recycling ratio, it's a huge amount. Because the Indian monsoon has a variability of only 10%. So you can understand 25% is a huge amount. And why it is happening? If you are considering the central India and other region, but you can see that around 25% recycling ratio actually you can see over the entire Himalayan belt, which is very, very important. And this is something also we need to, at some point of time, we need to investigate that in what way, if there is a change, climate change or some sort of changes, if there is a deforestation or something, then how does this, vegetation really, change in vegetation is really affecting the recycled precipitation and hence the total precipitation. That can be one of the very interesting science questions. But more importantly, you can see that the Gangetic Basin, which is one of the region which has a lot of agricultural activities, you can see that initially because the soil didn't have much moisture, the crop stages are actually at a very young stage. So the evapotranspiration is quite low, so the recycling ratio is quite low. But as it progresses, as the monsoon progresses, your soil is getting recharged with more moistures, and crop is at a mature stage. So a lot of evapotranspiration is taking place, and you are reaching around 25% of recycled precipitation. So yes, recycled precipitation is important. Land is playing a major role. It's mostly over the northern region, northern India and eastern India. And over Himalaya, there is a very consistent high recycling ratio. This is probably because the Himalayan region also receives very good rainfall because during the winter season because of western disturbances, and also pre-monsoon showers are also quite they happen quite frequently, and because of this probably there is a very good recycling ratio. Now the other thing is that what we also found is that these land contributions are not really impacting the mean precipitation. They're very important for extreme precipitation. We did a work where we have found is that if you consider the central India, there's an increase of extreme precipitation that is widespread. So during the monsoon, during the peak monsoon time, sometimes we find in recent days that there is a huge moisture surge that is coming from the Arabian Sea. It first hits Mumbai. We get affected first with a heavy flood kind of situation, but it doesn't stop here. It crosses the Western Ghat. There's a huge moisture surge. They don't get stopped now very easily by the Western Ghats, and they entered the Indian landmass, and they keep on creating extreme precipitation throughout the region. So essentially, the entire central Indian belt get extreme precipitation, and this has increased threefold. So if you are considering over last 50 years, threefold increase of widespread extreme precipitation has taken place. So what we tried to understand, what are the major contributors? What we found is that Arabian Sea is the major contributor. Next, we thought the second contributor will be Bay of Bengal, because normally this kind of extreme precipitation has some connection with some of the depression that generates over the Bay of Bengal. But what we have found is that Bay of Bengal depressions only drags moisture through this moisture surge, but they do not contribute much. But what happens, you can see that 26% contribution is coming from Bay of Bengal, but land contributes more than even Bay of Bengal. It's around 29%, around 30% of the extreme precipitation is contributed by land. So land is also very important, not only for mean precipitation, but even for extreme precipitation. Now when the analytical data or the analytical modeling says that, look, land is very, very important. So what we wanted to understand is that because we know that monsoon is one of the very challenging tasks for a model to simulate, and we know that our Ministry of Earth Sciences have CFS version 2. They have adopted climate forecasting system version 2 for operational monsoon prediction and forecasting, which has been taken from NCEP, National Center for Environmental Predictions. But of course, after that, Ministry of Earth Science has done a lot of work. IITM has done a lot of work in terms of improving the model so that we can simulate the Indian monsoon is a better way. Despite of lot of improvement, what we can see is that if you are considering this CFS-V2, this is the model, minus GPCP, which is the observed data set, you can see there is a huge dry bias, specifically over the Gangetic Basin and the Himalayan region. You can see that there is a huge dry bias. And we were trying to understand that why there is a huge dry bias and why it is so much over the Gangetic Basin. This is something which we are not very clear. Then, I had one student, her name is Anjana Devanand. She graduated in 2019. So what she wanted to understand is that, let's say if you improve our land simulations in the climate model, let's say if you simulate land in the climate model in a better way, does that improve? So that was the idea. And the other thing what you can see is that normally these models produce a lot of rainfall over the ocean. You can see ocean, there is blue. That means there is a weight bias. In ocean, there is a blue, and land, these models are producing less rainfall. So the idea here is that can we improve that? So what we did, so the idea here is that understanding the problems I was saying with regional land surface representation in a model and addressing them in a regional framework will improve the forecast skills. So for that, what we picked up is that we have picked up the model, which is the regional climate model, which is known as weather research and forecasting model, and this was coupled with community land model. So WRF has an atmospheric component. So I'm not going into details, just telling you this, and this is the land model. An atmospheric model is sending precipitation, wind, temperature, pressure, humidity, solar radiation, etc. to the land model, and land is sending back latent heat flux, sensible heat flux, moisture flux, albedo, etc. Now the land has a standard hydrologic model, and it also has a strong vegetation component. But for that study, what we have considered, that vegetation we consider prescribed to be constant for the entire period, and we tried to understand what exactly is happening. Now this is the region, and over the Gangetic Basin, we have collected as much information as possible, and very nicely we represented over the. I mean, she did it nicely. And then this was the original bias. You can see over Gangetic Basin, there is a huge bias. This was the original model. Then this model output, this was a global model. We put it in a regional model, which has a better land component. And when we run it, what we have found is that when we improve, of course, this region we could not improve, but this region over the Gangetic Basin, when we improve the land representation, you can see there is a sudden drop in the bias. You can see that earlier mean error was 68%, which is reduced to 25%. This is with community land model. But we wanted to make sure that this is not really a coincidence that just because of the model change it is working. So we wanted to try with another model, which is NOAA LSM, which was coupled with work. We further found some more decrease in error. That means RMSE is improving and so on. So you can see that your error is now only 13%. So yeah, you can see that the errors are getting reduced because of improvement in the land model. So we are trying to understand why it is happening. What exactly is the reason behind it? Then when we looked into it, the first thing what we have found is that, let us look into this figure. So you can see these are the observed contribution. Okay, these are the observed contribution which you have got from the analytical model. So the first one is the contribution from the oceanic sources. Second one is the recycled precipitation, and third one is the contribution. Green one is the contribution from all the land sources together over the Gangetic Basin. And if you are considering the model simulations, we can see that of course land contributions are low. That is quite expected because land representation is not very good in CFS-V2. But what we are finding is that even the oceanic contribution is also underestimated by the model. So we are trying to understand why it is happening. We tried with different resolution, everything, we are getting consistently same result. It's not the resolution, there is something else. Then we used our modeling approach with ERA, and what we have found is that now you can see that it improves the land contribution. You can see that red line and green lines, they are actually matching. So essentially land contributions are improved, and that is quite expected because you have improved your land model. But what we are not sure, we're kind of puzzled that initial part of the monsoon also, even oceanic contributions are much better. Even the later half also, you can see that earlier the model has like this. Now with with a land model, with a better land contributions, these things are improving. Then when you looked into it, what we have found is that because land didn't get much of importance, what happens, the Himalayan representation was also not very good in CFSV2. And what was happening is that, when your monsoon takes place, is land region gets warm compared to the ocean, and because of their ocean to land, there is a moisture surge. That is the mechanism of Indian monsoon. And why ocean, this land gets so warm? Because Himalaya normally blocks lot of wind, that is the lot of circulation that comes from the exotropic, and so cold airs are kind of blocked by the Himalaya. But what is happening when you do not represent Himalaya properly in the climate model? It allows lot of cold air to enter Indian landmass. As soon as the cold air enters during the summer season in the Indian landmass, your landmass gets cold. When the landmass gets cold, the land to ocean temperature difference does not develop. When they do not level up, the wind cannot go from ocean to land. And because of which you can see, now if you go back to, sorry. Maybe I'll go here. Yeah. Now if you go back to here, you can see up to this point there was not much of problem. The problem starts from here because lot of cold wind are coming, and that's why this region is cold. Because this region is cold, the moisture cannot enter the landmass. As moisture cannot enter the landmass, the moisture is taking the correct path, but it cannot enter, so it gets precipitated over this region. That was the problem in the model. But as soon as you represent the Himalayan representation, you represent Himalaya in a better way in the model, the entire system is performing very well. So, and you are getting a lot of monsoon characteristics are actually becoming very, very prominent. That's one of the thing. And second thing, of course, the recycled precipitation. Yeah, so this is something, and in fact, this work when it was published in Geophysical Research Letter, the GRL editor considered it to be the research spotlight of American Geophysical Union for that year. So this got a huge attention. Then the third thing what Anjana was trying to understand is that what are the impacts of, so we understood that land is very important, and at the same time we know that our agricultural intensification is taking place. Because of agricultural intensification is taking place, there is a lot of irrigation that is taking place over the in the Gangetic basin, and there is a lot of groundwater irrigation that is taking place. And you can see the groundwater fraction is very high over India, and in the Gangetic basin the irrigation is very high. And you can see the increase of Kharif season irrigation water use. You can see it's quite increased. And one of the major problem is with Indian type of irrigation is that if you go to the Western countries, mostly they measure the soil moisture, and based on the soil moisture measurement, they apply irrigation based on the water need. But in India, the farmers are not really rich to really buy a soil moisture sensor, measure it, and so on. So what they do when we interact with the farmers over in the Gangetic basin, over Bihar region, what we have found is that the farmers normally irrigate when they could arrange some money, from some money lender or someone, buy some diesel. So they have to use the diesel. They just pump the groundwater and put it on the farm region. That's one of the thing what we have found. So and second thing is that there are a lot of regions which are essentially the paddy. Paddy means you have to keep it in a submerged condition, which is an entirely different kind of scenario compared to what is there. Because in Western countries, mostly it's maize or some other things, maize, barley, this kind of crop. But here we are essentially talking about paddy. And more than 50% crop area is paddy field. So it's very important to understand what are the impacts of paddy field. Now, one of the problem that is there in the global climate models is that there are a lot of models which has its own irrigation component. But all these irrigation component, what they consider globally during the summer season is the best time for the agricultural activities. So during the summer season, the agricultural activities increases, and the irrigation is being computed when the soil moisture goes below a certain value. Now, what is happening if you apply this model without properly representing the India specific condition, you will find that lot of irrigation that is taking place during the pre-monsoon season, which is not really a proper crop season. Because during that time soil moisture is dry, they keep irrigation. Community art system model, you will find that for different land use, land cover, consistently you are getting a very high irrigation during the April, May, June, which is not really a very good crop season. And because of this, probably you were aware that there was a paper which came in Nature Geoscience by IIT Gandhinagar, few scientists. They published a paper with sort of foreign collaborator, and they showed that pre-monsoon irrigation is actually increasing the wet heat stress over the Gangetic basin, simply because from the irrigation we get lot of moisture. But that's actually wrong, because they used a model which has been just blindly picked up from the Western country and blindly used. So Indian data was not properly used and Indian scenarios were not properly used, because of which you get a lot of irrigation and a lot of increase in humidity. But ideally it's not the case. Ideally it's an entirely different thing. So very important to understand the correct representation of the crop cycles in the model, correct representation of the paddy fields, correct representation of the farmer's behavior, etc. Which is a very challenging task though, because you have to understand everything and you have to write your own code and then put it in there in those models and typically run it. It's a challenging task, but Anjana somehow wanted to do this, and Anjana did develop that model, and then she did 3 runs. One is that control run, where there is absolutely no irrigation. The second one is the realistic condition, where we collected the irrigation data from agricultural sensors and we have used the paddy fields and run the model. And third one is the idealistic irrigation, if you pick up blindly from the one of the Western country model. So if you do real condition, IRR minus idealistic condition, which is taken from typically from a Western model, then you'll see a lot of difference in the irrigation. So over the Gangetic basin, there is a lot of difference. And so you know, for this thing, we have done a lot of modeling thing in the community land model. I'm not going into details because it was a complicated task, but she could develop the equation, solve the equation, partial differential equation, and put it in the model, add the module. But everything is available now online. So anybody who wants to use this module, they can use the model. And it was published in GRL, Geophysical Research Letter. Now, one of the very important thing what we have found, as we know that September is that month when we expect that a lot of recycled precipitation is there. So when we have control run, realistic irrigation and idealistic irrigation, you can see that in proper irrigation representation, you'll find that the rainfall band during September is moving northwest, which is not really happening in ideal irrigation. So you can see in ideal irrigation, your rainfall band remains here. But as soon as if you do a proper irrigation, if you change your irrigation practice, or if you, because of Indian irrigation, what is happening, this rainfall band is moving towards northwest. And this has been actually happening over last 20 or 30 years. If you see, these regions during the end of the monsoon is receiving high rainfall, which was not earlier happening. And that is because of the irrigation feedback. That shows that whatever water management practices you are doing it on land, that also has significant feedback to monsoon. So monsoon is not just large scale processes. It receives a lot of feedback from the vegetation, from the human activities, and so on. Now I'll come to the feedback from time varying vegetation. This is also another thing which has been done by one of my student. His name is Sachin Budakati. So and with the help of another student, Tejashvi. So let's say if you are considering the hydroclimatic system. So let's try to develop the hypothesis first. And this hydroclimatic system is continuously going through some variability and changes. Now, whenever there is a climate variability or changes, the plant tries to strategize itself. Like let's say there is a drought condition, there are many plants who tries to reduce their leaf area, reduce their plant, reduce their leaf area or reduce their leaves, and because of which there will be land atmospheric feedback or land atmospheric changes feedbacks will reduce, and so on and so forth. Or plant try to acclimatize when there is a climate change and so on. So that will change the interactions with water cycle, like change in ET and so on and so forth. So idea here is that we are trying to understand what is the feedback of this kind of changes on the hydroclimatic system. So of course, because of climate variability and changes, there will be changes on plant. But if there is a change in the plant, what will be its feedback again back to the climate system? We are trying to understand that. And for that purpose, again, we have used WRF-CLM. This is now fully accepted, sorry. So what we did is that this is the warp CLM, and here what we tried to do, we have picked up the one of the Moody's leaf area index data set. One thing what we did, we considered the conventional approach where we are considering the average leaf area index, because you always assume that vegetation is not probably playing a major role for monsoon. So we consider the constant vegetation for monsoon always, even for the our operational monsoon model also we have the constant vegetation that we put. So this is the constant vegetation, which is known as climatological leaf area index, which we put into the work CLM. And the second one from Moody's LAI, we picked up the varying LAI, that is varying leaf area index. Every year it is getting changed, and that is also we are putting in work CLM, and we get lot of variables and then apply the process network kind of approach to understand what exactly are the changes in the atmospheric processes because of changing vegetation pattern. So we are not saying because of atmospheric changes what are the plants change. I'm trying to say is that because of the change in the plant, what are the change in the atmospheric processes. That's what I'm trying to understand. And we picked up Indian region, of course, and we divided
क्लाइमेट
into six.
वेरिएबिलिटी मॉडल सिखा रहा है सारे कैसे
Sorry. I think she. So if now there are multiple regions. Now if you plot this is the observed rainfall, the blue one. Now if you are considering climatological area, you will find the R value of 0.385. Of course, it's not very good. These are free climate model simulations. But if you are considering varying area, suddenly your R value is improved. That's one of the important things. So if you consider the perturbation in vegetation and represent them in the model, so it is actually getting improved. And the highest improvement is over the Gangetic basin. You can see that over Gangetic basin, there is a very high improvement. For other regions, of course, it's very difficult to find out. Let's say for Jammu and Kashmir, it's very difficult to find out because our own observation stations are also very less. Even Northeast Hills, you can see there is a good improvement and so on. Northeast India also improvement, Northwest India. So everywhere you can see that most of the regions, there is a good improvement of, when you are using the vegetation feedback properly. Now, what we try to understand, of course, that could have been a end of the study where we say that if you improve vegetation, your monsoon rainfall is increasing. But what we wanted to understand is that we wanted to understand using a information theory based approach, how it is really improving and what exactly is happening because of the improvement, or what exactly happening between the connections between land and atmosphere. So what we use the theory which is known as information theory based process network. In fact, the same theory is being used now. Both Shandipan and I together, we are working for the Pinok ecosystem. We're using same theory at a even local level, what exactly is happening. So I'm not covering that part. One of our paper is under review on that. But what we'll do, we'll just focus on this specific work. So when you're talking about information theory, the first thing is known as entropy. Information theory entropy. So entropy is the measure of uncertainty. Now, or it's sort of showing the importance of the information. So I'll tell you how does it show the importance of information. So let's say, I always give this information. Let's say if you're living in a city, okay, or let's say you are now in Mumbai. You are at IIT Bombay campus. IIT Bombay campus is around 30 minutes to 40 minutes drive from the Mumbai airport. And you have a flight during, let's say, around 12 noon. So you have to reach by 10 a.m. If you have to reach by 10 a.m., you ask me, and I'll say that, oh, you have to reach by 10 a.m., you have to start at 7:38. Otherwise, there will be huge traffic. That's the office time. You will say that, okay, sir, I know that because Mumbai, there is a huge traffic. There's not, of course, you will not say directly, but you know that that's not a very important information. So you know it very well. But let's say if you have a flight in the midnight at 12 midnight, and if you have to reach by 10 p.m. and I'll say that, look, today you should start at 6 p.m. or 7:30 p.m. because there is a huge traffic because of some metro construction or something is going on or some road is blocked. Then for you it will be a very important information, because during the midnight time you should not expect very high traffic jam. Then we will give a lot of importance to it. So when do we give importance to an information? When the information is having a lot of surprise. So now what does it mean by surprise? High surprise means low probability. Now, if you are considering log 1 by p, log 1 by p is the measure of the surprise. So there is a huge surprise, that means low probability. Log 1 by p is a measure of surprise. Now the probabilistic mean of the surprise, that means p multiplied by log 1 by p, this is known as entropy or Shannon's entropy. Shannon in 1946 or 56, he developed this theory, which is now widely used for communication network. And this is something what we try to do even for ecosystem network. Now, if you are considering the joint entropy, let's say there are two variables x and y, the joint entropy will be given by this. And mutual information means the information content by two variables x and y, their intersection, which is again following some same kind of probability theory, hx plus hi minus hxi. So this will be your mutual information. Now then, coming to transfer entropy, this is what is very important. Transfer entropy is something that tells you about causality. So what does it mean by causality? Let's say I'm interested in what is happening to x at time t plus 1. Now I'll try to find out how much information from y, s means past of t plus 1. So how much information from the past of y is coming and reaching xt plus 1. Given that the same information is not coming from the past of x. So whatever information x is receiving now, that is not coming from the past of x, but exclusively coming from past of y. That means only this part. If this is coming, that means past of y is affecting the future of x. That means y causes x. So this is what is process network. That means a variability y is modulating the variability of x. So y causes x. So if there exists a transfer entropy, that means y causes x. And that it has to be statistically significant if y really causes x. Now when we applied this information theory based approach, what we are finding is that these are the 7 regions which we have considered the land variables. This is starting with sensible heat flux, soil moisture, evapotranspiration, latent latent heat flux, and so on and so forth. And then if you check them, you can find that all these land variables are sending information to the precipitation over different regions. P1, P2 is P3, P4 is not getting, P1, P2, P3, P5, P6. And these are the links which are there for 60% of the years, minimum 60% of the years. If the links are present, then we are showing that link. You can see that all the land regions are actually important, and they drive or they change or they cause changes in the monsoon rainfall. So they are causing changes in the monsoon rainfall. That means land variables are important. Then and this is what, in a different way, we have wanted to show that how strongly connected they are. So you can see that, if you look into this, if you consider all the variables together, the network looks like this, how complicated it is. But, we wanted to represent in a better way, where we are showing that these are essentially the source variables, which are land variables, and these are the sink variables, which are receiving. So these are receiving transfer entropy, and these are sending transfer entropy. Now, the other thing what we wanted to see is that we wanted to see what exactly is happening in the drought years and what exactly is happening in the surplus years. Now, this is very interesting what we have found. Drought years means moisture deficit years, the stress period. You can see 2009 and 2014 are the drought years. In the moisture deficit periods, the number of links from total number of links and the number of links from land to atmosphere is very high, which is not happening in the surplus links. And this is consistent. You can see except this variable, for all the variables, you can see for all the land variables, this is quite significant. You can except albedo. So sorry, except albedo, if you consider soil moisture, soil moisture, evapotranspiration, and so on, you can see that this is actually an LAI. This is LAI, this is the evapotranspiration, and this is the soil moisture. For all the cases, you can see that surplus years, deficit years are having more number of links compared to the surplus years. Now, if you remember, I was explaining the example that under the stress period, let's say if 5 friends are crossing a river and river does not have current, you can actually cross by walking. Let's say the water level is very low. But if there is a huge current, all the 5 friends will hold each other's hand and cross the river. In the same way, what is happening under the deficit period, land actually extends lot of support to the atmosphere. And because of which you can see more number of links are being generated from land to atmosphere. So land drives many of the monsoon processes during the deficit years. It generates a lot of recycled precipitation to sustain the monsoon. And this is what consistently is happening over the drought years, which is not really happening over the surplus years. Then what we wanted to test is that, let's the final kind of slide. We wanted to find out even within the monsoon how the intraseasonal variations are getting affected. That means during the entire monsoon season, you do not receive heavy rainfall in all the days. During some days you will get heavy rainfall. During some days you will get almost no rainfall. They are known as active and break period. So what we wanted to understand, when central India has an active and break period, if you change your LAI, how does it affect? So what we are finding is that if you consider most of the cases, you can see that during the active period, the rainfall increases because of the vegetation feedback. During break periods, it get reduces. So you can see that vegetation is actually playing a major role in terms of even perturbing at the intra-seasonal scale as well. Of course, this is a very recent work. We have to do some more work. And it starts showing some signal that it does not really affect much the timing of the active or break period. But during the active and break period, you can see there is a lot of difference. So these are essentially, I will explain this one figure. This is the varying LAI, this is the climatological LAI. And these are essentially the active and break period. Active period is shown as blue and break period is red. This is for 2005, these 2 years. So you can see that mostly blue lines are actually overlapping on each other. So they are not really, red lines are overlapping on each other. So they are not really impacting the location or timing of the active and break period. But within an active and break period, if you find out the difference between the two simulations, you will find that there is a lot of difference. And these differences are more during active and break period. That shows that vegetation, under stress vegetation, being it a very high rainfall or being low rainfall, the vegetation feedback becomes more and more important. So that's all from my side today. So I'll conclude like, I'll always say this, that, the components of our system are connected through links. And if there is a perturbation in one of the component, this component try to send this perturbation to other components through these links. And hence it's very important to understand not only the forcing links, but also the feedback links. Feedback is very, very important. So thank you. Thanks for your patience. If you have any questions, I'll be happy.
Sorry. Why do you explain this? That is happening right now in Delhi and northern India is being centigrade and north India is climate. So how is it?
So I would say that these two patterns are entirely different. So if you're considering the northern India at this moment, what is yeah. So typically, during the summer season, we expect some sort of a pre-monsoon showers. And what happens when there is a pre-monsoon shower? There's soil moisture. There is a little bit of soil moisture. There is a little bit of cooling because of the moisture evaporation and so on. But typically, in this pre-monsoon, we never received a shower. That's one of the things. So there is a prolonged dry period. That's one of the reasons. The second thing is that we are actually working on this, this heat wave part. Not really specific to this heat wave. We started actually long back from November, December. We have started working, and we are finding this that during monsoon there is an interseasonal variations of active and break period, right? During the heat wave condition also, because of the Rossby wave, what is coming from the other side, there is an active and break cycle that goes, because of which you'll get a heat wave followed by a cooling period, and cooling period are associated with little bit of rain. But what is happening, this prolonged heat waves actually there because of the Rossby wave pattern which is happening in the upper latitudes. Because of that, there is a very long spell of heat waves which was there, and there was no, normally this hot period is followed by a cold period which will come from west to east. The cold period was not visible, and because of which there is a consistent heating part, and the northeastern part is quite kind of, I mean, this is something which happens actually, the shower, but the showers are becoming more and more extreme, the pre-monsoon showers. If you're considering Bangalore rain, it was very extreme. Northeast also, it's very extreme. So extremes are increasing, we know, but can you really attribute to climate change? That will be a different story. But altogether, what we are seeing is that extremes are increasing, being it a seasonal extremes or it's a pre-monsoon extremes or post-monsoon. Exactly. Exactly, exactly true. Yeah. It's normally nor'westers or the cyclone, but it doesn't reach the northeast that bad. So this is just pre-monsoon shower, which becomes a very extreme kind of condition.
So not climate change, but it is something.
We don't know actually. We can really attribute it to climate change or not, that we don't know. We have to do a lot of simulations to really find it out. There is a method which is known as detection and attribution, by which for any event you can actually find out whether they are because of climate change or not.
Yeah, please, anybody else?
I have one query.
Yeah.
I'm not in the same field, but I found this interesting that the land contribution in rainfall in the map which you have shown.
Yes, yes.
So, whether the texture of the soil bed, because the moisture evaporation will be affected by
True,
the.
true, true.
So this factor is also being estimated, used as a factor in your model.
Yes,
You
yes.
are taking
Yes,
this
yes.
soil
Column, soil parameters are being considered
because
in the land model. Yeah.
Wonderful presentation, sir. And any relation between vegetation and this extreme events is it possible? Because number of conditions we are seeing that the vegetation led to monsoon and
Yes,
others.
yes, yes.
Any relations between the related to vegetation and anything?
That is quite possible because when you with Roxy, when you are working with the nature communication paper on the widespread extreme over the central Indian belt, we never. So what we wanted to find out is that it's essentially the Arabian Sea. Of course, Bay of Bengal, the depressions are being generated, but it's Arabian Sea which is actually pushing the moisture. It is very warm. It's pushed a lot of moisture, so the western belt, so the entire central Indian belt is getting a lot of extreme rainfall. But we have suddenly found that the land contributing 29% of the moisture. We are actually surprised. That was the reason, because of the moisture component thing which Amay did. Because of that, nature communication took it. So nature communication said, this is very interesting. The land is contributing contributing so much of moisture to the extreme. So it's quite possible, because for Himalayan region, the land atmospheric interactions is kind of not very well known, not very well researched. So I think there is a huge scope of research to really understand what is the role of Himalayan vegetation in terms of generating rainfall, because we always receive a very high recycled precipitation even at the starting of monsoon also.
Actually, not a question,
Yeah.
but for my knowledge.
Yeah.
Because again, the vegetation types is, great changes are found in the Indian country.
Yes.
You see, even sometimes you will find equatorial to subtropical and tropical and subtemperate. So is there, their effect would also be there? in
Should be.
rainfall conditions,
Should be. Yeah.
Should
Should
but
be.
in the Indian Himalayan region, only forest is dominating
Yes.
compared to other forests.
Yes.
So it has been some peculiar impact on rainfall.
Could it be? I mean, it could be. Actually, this is something which we have to really understand what exactly. So, of course, with Shandipan, we are trying to understand at a point scale what is happening, what will be the land atmospheric feedback, but more on the carbon cycle. But what my plan is that, of course, over a large region, over the large Himalayan region, we need to find out that if you represent the better vegetation condition and really run a model, then what exactly is happening, whether the extremes are getting more or extremes are getting less, or even the mean rainfall, how the recycled precipitation is changing. There are actually a lot of research which needs to be done to understand the role of Himalayan vegetation in terms of keeping the ecosystem working or keeping the water cycle working.
Once we had a discussion about some of the students who started working on the distribution of vegetation pattern and feedback.
Yes.
I remember, I think it was years back.
Tejashvi.
Someone was actually started doing the same thing. Sir, one of the students who was looking after the same thing. How would the change? We had a telephone discussion that the vegetation type of Western Himalaya is
Yes.
kind of different than after
Eastern Himalaya. Yes.
But, then somehow I don't know, it was never completed.
Yeah.
But someone was looking after the fact that if the vegetation type changes, whether the interaction is also changing. If we are having a similar interaction between precipitations and vegetation types over Western Himalaya and Eastern.
In fact, Tejashvi did that work, some work, not related exactly that work. So he wanted JOH paper, where he wanted to understand that what will be the role of memory from western to eastern. So there are a lot of western has a higher memory compared to eastern.
Yeah, but that was not linked with vegetation.
No, that was not linked with vegetation. That was so.
It was a generic relationship between other than.
Another important point from your presentation was that this cycle range.
Yeah.
So that is a very good concept, I think.
Yeah.
No, this cycle.
Yes.
Could you highlight a bit more on that?
Yeah. So recycled component is let's say if you have this region, of course we need to consider considerably large region because point scale we cannot really found. So if we are considering a considerably large region, so what you can find is that the evapotranspiration that is being generated from that land, again it goes back to atmosphere and again it gets precipitated. That is what is recycled precipitation. And recycled precipitation to total precipitation is known as recycling ratio. Now, if you are considering one of the paper which published in Poster et al. By 2004 by ETA Zurich, so they did a global analysis and they have just, because it was the first global analysis of land atmospheric feedback, it got a lot of attention. It was published in Science and they showed major blocks in Amazon and there was another major hotspot area over the Indo-Gangetic basin, but nobody really cared about it. It was there for a long time. Then then Praveen Kumar of UIEC and Praveen Kumar came to IIT Bombay. We had a long discussion about it. Then we together took a joint student Amay Pathak, who was co-supervised by Praveen, and then we together developed this. And then what we found is that over the entire Indo-Gangetic basin, your your recycled precipitation is actually around 25%, specifically during the end of monsoon, because end of the monsoon the crops are at mature stage and so on. But when we always focused on the Indo-Gangetic basin, to be very frank, when Shandipan and I discussed, and then we thought that it will be over Himalayan region. I just wanted to look into over the Himalayan region what was the recycle component. When I looked into the figure, I found it very interesting that in the entire Himalayan belt, it is consistently 25 to 30% for the entire monsoon, which is very important, which we never looked into it. I think at some point of time we really need to look into it. That means the vegetation over the Himalayan region is playing a major role, is contributing 25 to 30% of the rainfall, which is very, very important, I believe.
As compared to the average.
As compared to average of the, yes. Yeah.
That's very interesting.
That's very.
And again, is there any difference between Eastern Himalaya to Western Himalaya?
At this moment, maybe we need to look into more carefully. At this moment, I found that it's a kind of whole grain, but let's say if you pick up on the entire Himalayan region and do the color mapping, then we can see that the color differences.
Yes.
That we haven't looked into it. So as I said that, I mean, to be very honest, that just before the talk, I looked into it and then I found that over the Himalayan region is very high.
It is really very good nature, and I think that plan is solved and
So you were talking about one systems,
Yeah.
networking system and non-networking system. So my first question is that both kind of systems exist in nature.
Yeah.
Non-networking and networking.
No. It's always network system. The non-network system normally do not exist.
Okay.
So essentially all of them are connected to each other. It's a big network. But what we do, unfortunately, when the atmospheric scientists, they work, I mean, initially they work in silos. So they are not really interacting with the atmospheric scientists. Atmospheric scientists does not interact with land scientists. Land scientists does not interact with the ocean scientists and so on. But this needs to be done together. That's what is.
You were saying when the deficit year occurred, drought year,
Yeah.
there were more links generated. But you said that more links means stress will increase. More resisting links will increase.
Yes.
And once threshold will reach, it will be a sudden drop. So what would be the sudden drop in this case? When
I'll show you. That was the Streeter's first figure, which that's why I like this figure very much. So you can see here, you can see that there is a vegetation. Let's say it follows like this with vegetation. Of course, here vegetation is probably playing a major role. We don't know what is happening. This is a schematic figure. But what is happening when it crosses the threshold where vegetation cannot really exist, then you can see that precipitation suddenly drops from here to here. So essentially, precipitation drops from here to here. It just drops like this. So when it drops like this, that means the recycle component is all failed actually. The system broke down. The system is no longer this system.
So this is depicting the second one, the state and stress.
Yes, exactly.
And the first one is kind of idealistic situation.
Exactly. I mean that is not really idealist. I'll say that's the way we looked into atmosphere till now.
So please, Habiti, please
Yeah. Thank you. Yeah.
And the work, the sap flow work which we are doing, that is what I was asking. That which is differentiator, because you are taking one.
Yes,
So that is also one of the.
it is point scale. What Professor Ghosh was saying that on a global scale, it is very hard to see what is the role of is also very localized. We are getting transpiration. In case if we have a network of measurement across the Indian Himalayan region for the similar kind of species, or maybe for multiple kind of species, it can be extended. Right now, I think we are mostly focused on carbon part in terms of interactions, not looking after on the recycle specification. But that can be done. I think I have few other questions, but maybe time is short, so I may have discussions with you. On thank you, sir. नहीं, sir.
Okay.
और किसी का
So, is anybody left
नहीं left
who is very curious? ऐसा नहीं है कि अपने दिमाग में लेके जाए, ऐसा तो नहीं है कोई? One chance? No. But anyway, this is a very informative lecture, and as well as brainstorming to the youngsters to think on this direction too, along with our research, routine research. And I would say that definitely it has enriched our knowledge and all of us knowledge, and definitely our colleagues would keep in mind while they are working, and they should not work in isolation or silo, what Professor Ghosh told, because a lot of things arise when we connect one component to other component, and this is the concept of land and atmospheric interactions. Although I have also worked personally in atmospheric sciences, and I have a multidisciplinary approach, but I think today I also got some new things from you, and definitely in coming research that will be beneficial. Likewise, I expect from my colleagues that they will keep in mind and they will follow such type of research in coming days, which has a greater importance. And especially when we are talking about the model, or when we are talking about the climate change and vegetation index or vegetation modeling or monsoon, because our country is totally dependent on monsoon rain, and our economy is also based on that monsoon. So this topic is so important that I can't say anything, and I am beyond the words. So thank you, Professor Ghosh, that you, and within a short notice, probably you might have accepted this invitation. And thanks also to Dr. Sandeepan, who could organize this session. And it was really very nice to see you all people. And with this, thank you very much.
Thank you so much.
आपको कुछ और तो नहीं करना?
I mean, I'd like to say that if anyone have any questions or anything, please write to me. I'll be happy to answer the queries and collaborate. I mean, of
just
course,
write in Google Professor Subimal Ghosh, Dr. Subimal Ghosh, you will get his email ID.
हाँ, और आप शेयर भी कर दीजिए आपका ईमेल वगैरह
वेबसाइट में है हम लोग एक्चुअली हम तो आजकल आशुतोष ने सारा वेब में डाल के रखा है तो एवरीथिंग इज इन वेबसाइट
हाँ दे दीजिए सो थैंक यू वेरी मच
thank you so much. Thank you.
ओके प्रोग्राम
अभी हम लोग फैमिली दिन
अच्छा अच्छा ये भी डॉक्टर संदीप का लाइट प्लेस है मैं भी चाहूंगा वहां जाना
कैसा है अच्छा